Imagine a world without humans. No cities, no roads, no electricity, no internet. A world dominated by colossal creatures that had roamed the earth for over 165 million years. To put that in perspective, the time between when the last Stegosaurus lived and the first Tyrannosaurus lived is longer than the time between the Tyrannosaurus and you. They were the undisputed rulers of the planet. And then, in the blink of an eye, geologically speaking, they were gone. Welcome. Today, we aren't just going to talk about how the dinosaurs died. We are going to build the timeline of that single, catastrophic day. We are going to separate fact from Hollywood fiction, explore the global crime scene, and look at the surprising survivors who inherited the Earth. We are going to travel back 66 million years to the end of the Cretaceous period. This is the story of the fifth extinction. To understand the magnitude of the extinction, we first have to understand what was living right before it happened. The late Cretaceous was a world very different from ours. It wasn't just a swampy jungle everywhere, as old cartoons might suggest. It was a diverse planet with seasons, forests, and plains. First, look at the map. The continents weren't where they are today. Due to plate tectonics, they were drifting apart toward their current positions. You had North America, but it was split in two by a massive body of water called the Western Interior Seaway. This sea stretched from the Gulf of Mexico all the way up to the Arctic. India was an island, a massive continent-sized landmass floating alone in the ocean, speeding toward Asia. This isolation is crucial because it allowed unique animals to evolve there. The climate was warm. There were no polar ice caps. None. Imagine the idea of Antarctica having forests and dinosaurs because it did. Sea levels were hundreds of feet higher than they are today, flooding the low-lying areas of continents. This was a greenhouse world, with high levels of carbon dioxide in the atmosphere. And the animals living in this world? They were spectacular. In North America, you had the three-horned triceratops grazing in vast herds. We have found bone beds with thousands of individuals, suggesting they moved in massive groups like modern bison. You had the duck-billed Edmontosaurus, which had complex teeth designed to chew the tough conifers and flowering plants that were becoming dominant. And of course, hunting them was the apex predator, the king, Tyrannosaurus rex. We used to think T-Rex was a slow scavenger, but modern science shows it had incredible vision, a powerful bite, and could likely walk at speeds that would let it outrun a football player. But it wasn't just dinosaurs. The skies were filled with pterosaurs like the Quetzalcoatlus. This thing was as tall as a giraffe when on the ground, with a wingspan of about 33 to 36 feet, the size of a small fighter jet. How it launched into the air is still a subject of debate among paleontologists. The oceans were ruled by marine reptiles, mosasaurs, which were giant, air-breathing lizards adapted to the sea, plesiosaurs, with their long necks and small heads, and giant ammonites, which were shelled creatures related to the modern nautilus. Some ammonites were as large as car tires. Life was diverse, successful, and ancient. These animals had survived volcanic eruptions, climate shifts, and asteroid impacts smaller than the one we're about to discuss. They were resilient. But nothing in their 165 million year history could prepare them for what was coming. For decades, scientists argued about what killed the dinosaurs. It's one of the greatest whodunits in history, with suspects ranging from the plausible to the ridiculous. Let's look at the prime suspects that were taken seriously by science. Suspect number 1, massive volcanism. Right at the end of the Cretaceous, in a region of India we now call the Deccan Traps, the earth was ripping open. It wasn't just a single volcano like Mount St. Helens, it was a flood basalt event. Imagine an area the size of France or the state of Texas spewing lava for tens of thousands of years, possibly even a million years. These weren't gentle flows, they were fissures erupting with such force that they built towering plateaus of rock. This would have pumped massive amounts of CO2 and sulfur dioxide into the atmosphere. This causes a 1-2 punch. The sulfur causes short-term cooling by reflecting sunlight, while the CO2 causes long-term warming. This would result in wild climate swings, acid rain killing forests, then a warming trend, then more cooling. Could that have stressed the dinosaur populations to the breaking point? Suspect number 2, gradual climate change. As the continents shifted, sea levels were dropping. This reduces available habitat. It changes weather patterns and monsoon cycles. If you look at the very end of the Cretaceous, some fossil evidence suggests that dinosaur diversity was decreasing. Maybe they were already on the decline, and the extinction was just the final push. Suspect number 3, the asteroid. This is the one we all know from movies. But for a long time, it was just a wild hypothesis. There was absolutely no proof, and it was considered a fringe idea. The idea that a rock from space could end an entire world seemed too much like science fiction. The debate raged until 1980, when a father-son team named Luis and Walter Alvarez made a shocking discovery. They were studying a layer of clay in Gubbio, Italy, that separates the rock of the Cretaceous from the rock of the Paleogene. In that thin layer of clay, dating precisely to 66 million years ago, they found iridium. Iridium. This element is rare in the Earth's crust because it's a siderophile, or iron-loving element. When the Earth was young and molten, the iron sank to the core, and it took the iridium with it. So, the surface has very little. However, iridium is abundant in asteroids and comets, which never underwent this melting process. The Alvarezes found a global layer of this element, like a dusting of space powder, exactly at the line where dinosaur fossils disappear. This line is called the KPG boundary. The K comes from Creta, the German word for Cretaceous, to avoid confusion with the Cambrian period. PG stands for Paleogene. They proposed a radical idea: an asteroid hit the Earth, vaporized, and spread this dust across the entire planet. But if that were true, where was the crater? If you throw a rock into mud, you find a hole. For years, the crater was missing. Geologists looked everywhere in the ocean, in the mountains, but found nothing. Then, in the 1990s, geologists working for the Mexican state oil company, Pemex, were looking for oil in the Gulf of Mexico, near the town of Chicxulub in the Yucatan Peninsula. They found a massive, buried arc of gravity anomalies. Gravity is slightly weaker over less dense, broken rock. They had found a structure. They had found the crater. A massive one. Chicxulub crater. It's over 180 kilometers wide, 112 miles. It was caused by an object at least 10 kilometers wide, about the size of Mount Everest. When you do the math on the kinetic energy, it hit the Earth with the force of billions of Hiroshima bombs. The energy release was equivalent to something like 100 trillion tons of TNT. The debate was over. The asteroid had found its crime scene. But finding the crater was just the beginning. The real question is, what happened next? What actually happened in those first minutes, hours, months, and years? To answer that, we have to look at the geology of the impact site. Let's set the scene. It's a spring day 66 million years ago. Recent research looking at growth rings in fossil fish bones from the impact site suggests it was spring in the northern hemisphere. The dinosaurs are going about their day. A triceratops is maybe grazing, keeping an eye out for predators. A T-Rex is patrolling its territory. It looks like any other day in the Mesozoic. In a fraction of a second, the asteroid, traveling tens of thousands of miles per hour, punches through the atmosphere. It doesn't even slow down. It penetrates the Earth's crust. It vaporizes instantly. The rock beneath it vaporizes too. It carves out a transient cavity, a hole 20 miles deep, punching through the crust and into the mantle. A blinding flash of light brighter than the sun ignites forests for thousands of miles instantly. If you were standing in what is now modern-day Colorado, the flash would have been immediately blinding and fatal. The megatsunami asterisk. The impact generates a megatsunami. Not just a big wave. Imagine a wall of water over a mile high radiating outward in a circle from the Gulf of Mexico. It scours the ocean floor, ripping up sediment and depositing it in a jumbled mess. It crashes into coastlines with unimaginable force, wiping out anything living in coastal plains across the globe. We find evidence of this tsunami backwash in strange sediment deposits all the way to what is now North Dakota. The ejecta and the heat pulse asterisk. Here is where it gets truly apocalyptic. The asteroid pulverizes and melts rock, flinging it into space in a cone-shaped trajectory.
The dinosaurs.
This material, now molten blobs of glass called tektites, arcs up and then falls back to Earth across the entire hemisphere. As it re-enters the atmosphere, friction turns the sky into a furnace. The atmosphere itself becomes the heating element of an oven. For a few hours after impact, the planet becomes an oven. The heat is so intense that it ignites wildfires globally. There is a fascinating site called Tanis in North Dakota where fossils show fish with tektites lodged in their gills, buried by the surge of water from the earthquake, and then their carcasses were charred by the heat pulse. Every dinosaur not in a burrow or deep underwater is cooked. The sky glows red. This is the first wave of death. Dash. If you survived the first day, perhaps you were a small mammal in a burrow, or a deep-sea fish you might have wished you hadn't. Because what came next was arguably worse, and it lasted for decades. The impact site in Chicxulub was special. It wasn't just random rock. It was a shallow sea sitting on top of a platform of limestone and gypsum. Limestone is calcium carbonate, full of carbon dioxide. Gypsum is calcium sulfate, full of sulfur. The vaporization of these rocks released trillions of tons of sulfur aerosols into the stratosphere. Along with the black soot from the global wildfires and the fine silicate dust from the pulverized granite, this debris formed a global shroud. It blocked out the sun completely. Impact winter asterisk. The planet went dark. Imagine the darkest night you've ever experienced, but it lasts all day, every day, for years. And then it went cold. Global temperatures plummeted. It went from a warm, lush greenhouse world to a freezing, dark wasteland. Some models suggest temperatures dropped below freezing worldwide for several years. For years, maybe a decade, photosynthesis ground to a halt. Without the sun, plants died. Without plants, the herbivores that survived the initial blast starved. Without herbivores, the carnivores starved. The food chain collapsed from the bottom up. It wasn't just dinosaurs, anything that relied on fresh plant matter died. Acid rain fell from the sky for months, created by the sulfur and nitrogen compounds, poisoning lakes and rivers. The ozone layer was destroyed, letting in UV radiation once the dust finally cleared, causing further mutations and health issues for survivors. This is the impact winter. This is what killed the non-avian dinosaurs. It wasn't just the blast, it was the starvation and the cold that followed. The large body size of dinosaurs, which helped them regulate temperature in a warm world, became a death sentence in the cold. They needed too much food that no longer existed. So, if the world ended, who was left? When we look at the fossil record just above the KPG boundary, the extinction event wiped out roughly 75% of all species on Earth. All non-avian dinosaurs died. The pterosaurs died. The marine reptiles like mosasaurs and plesiosaurs died. The ammonites, which had survived previous mass extinctions for hundreds of millions of years, finally vanished. But some life made it through. Who were the lucky ones, and what made them special? 1. The birds ***. Yes, birds are dinosaurs. They are theropod dinosaurs, just like T-Rex and Velociraptor. Some small, ground-dwelling, or waterfowl-like birds survived. Why? Perhaps they could eat seeds, which are tough, dormant packets of energy that can survive a nuclear winter. Maybe they could burrow or hide in water. Their high metabolism and small size also helped. 2. Small, burrowing mammals ***. Our ancestors were there. They were small, shrew-like creatures, probably nocturnal to avoid the dinosaurs. Their small size was their greatest asset. You need less food to survive. Burrowing protected them from the initial heat pulse and the freezing cold outside. They were likely omnivores, able to eat insects, worms, seeds, and plant matter that was rotting but still calorically available. 3. Crocodiles and turtles ***. They are semi-aquatic. The water may have buffered them from the most extreme temperature swings. Also, crocodiles are masters of survival. They can go months, even over a year, without food by slowing their metabolism. They are living fossils, living proof of this survival strategy. 4. Fish ***. The oceans were hit hard by acidification and the collapse of the food chain, but the extinction primarily targeted surface life and creatures on the seafloor that relied on detritus. Many open water fish and sharks survived. 5. Plants ***. It wasn't just animals. The forests died. But plants have seeds and spores. Ferns are often the first plants to recolonize disturbed ground. We see what is called a fern spike in the fossil record right after the impact, a time when ferns dominated the landscape before the flowering plants made a comeback. The survivors were the adaptable, the small, the generalists, and those that could wait out the storm. In the ashes of the dinosaur age, they found a world empty of giants, ready to be repopulated. The extinction of the dinosaurs was a tragedy for them, but it was an opportunity for us. It reshuffled the deck of life completely. With the large reptiles gone, the ecological niches were wide open. The surviving mammals, those tiny shrew-like creatures that had lived in fear for 160 million years, began to diversify rapidly. This is called an adaptive radiation. Over the next 10 million years, they grew larger, filled the roles left empty: herbivores, big predators, gliders, swimmers. They spread across the globe. By the Eocene epoch, we see the ancestors of horses, whales, bats, and primates appearing. This event, the KPG extinction, is the reason we are here. If that asteroid had been a few minutes later or earlier in Earth's orbit, if it had hit deeper ocean water or a different type of rock that didn't produce so much sulfur, the outcome might have been different. Dinosaurs might still rule the Earth, and mammals might still be hiding in the shadows, waiting for their chance that never came. Today, when you look at a bird on your windowsill, a sparrow, a pigeon, a crow, you are looking at a dinosaur. You are looking at a direct descendant of a survivor of the apocalypse. You are looking at a theropod. The asteroid didn't kill all dinosaurs. It just killed the ones that didn't fly. So, the story of how the dinosaurs died is also the story of how our world was born. It's a humbling reminder of how fragile life can be on a cosmic scale, and yet, how incredibly resilient it is on a biological scale. From the ashes of one world, another rose. And that world eventually led to us, sitting here, wondering about the creatures that came before. Thanks for watching. If you want to dive deeper into a specific survivor, like the journey of the mammals from the shadows to dominance, click the video on screen now.